So we start. Speaker is Paula Tuzón. She is not a misspelling, it's from IFIC, Institute for Physics.
Corpuscular Physics.
Institute for Física in Valencia. She's a PhD student at Valencia. She's working with Antonio Pitt, working on particle physics and Higgs, something about the Higgs. She has taken the challenge to come here because she's interested also in complex systems. So she's willing to talk with any of you who find her work interesting and wants to learn new fields. She has taken the challenge to tell us what the Higgs particle is. She knows that we are not listening to particle physics, and then she will explain from the bottom up what the particle, what the Higgs is about.
Thank you. Well, first, thanks for inviting me here. It's a pleasure to be in Mallorca. Actually, it's my first time. So, my talk is entitled Physics Beyond the Standard Model, adding one more Higgs to the puzzle. This is the outline. First, I will try to introduce you what we call the standard model of particle physics, what all physicists agree that is the model that describes the fundamental particles. Then I will give you also another overview of what this model cannot describe, why this model is the correct way but is incomplete. We need more physics, we need to go beyond. And then how the LHC, the Large Hadron Collider, which is built in Geneva, can help to that. And finally, I will present you a particular way of enlarge the standard model, going beyond the standard model, which is adding one more Higgs to the puzzle. And in particular, finally, I will present the aligned to Higgs added model, which is what I am working on since last year now. So let's start with the standard model, the pieces of this model. The standard model tries to answer some basic questions, basically tries to explain how the basic contents of matter behave. Physicists always have thought that this question is very important. Actually, when Schrödinger was asked about what he would leave as a legacy to a possible new civilization, just in case the humanity was killed, he answered that he would write in a small piece of paper that matter is made of atoms, as a very good starting point of understanding what's happening. But we know now that this is not the most fundamental species, but we have some fundamental particles that are below this whole table of periodic elements. This table is divided in fundamental particles and interactions, basically. The interactions are also particles, but describe how the other particles interact. Okay? Fundamental particles are of two types. We have quarks, which are the fundamental components in the nucleus of the atom, and leptons. An example of a lepton is, for example, an electron. Okay? As I said, the most famous lepton is the electron. Then we have the muon and the tau, which are exactly the same as the electron, but a bit bigger. And we have here the neutrinos, which interact very, very weakly. They are like the phantom of the particles. Then we have the quark sector. Here, to summarize this table, all the particles that are in the same column have the same charge, and all the particles that are in the same row, we say that they are a family. Okay? So from here to here, there's no difference but the mass. We say that we are changing family, they are exactly the same. Then we have the bosons, which are the particles that describe the interactions. For example, we have the photon, describing the electromagnetic interaction. We have the gluon, that describes the strong interaction, which is an interaction that happens between the quarks. Then we have the W and zeta bosons, which describe the weak interaction, also happening inside the atom, and describe, for example, the radioactivity. And there's some interaction that is not in this puzzle, which is gravitation. And it's not in this puzzle because we don't know how to improve. It's just that. We have a lot of work to do here. And finally, we have the Higgs that interacts with the vacuum. But let's don't say more for the moment. what is the board of this species? How to describe this species? What is the theory that it's going to give the interactions and the particles description? Okay, we want to display the basic contents of matter, and basic contents of matter are at very small distances. The Compton relation tells us that very small distances implies very high momentum. So we need one theory that describes the world of the very small, which is quantum mechanics, plus a theory that describes the world of the very fast, which is relativity. What do we learn from quantum mechanics? From quantum mechanics we learn, we know the notion of probability. We know that particles are described by operators that give the Schrödinger equation, and the Schrödinger equation describes how a wave function is moving in space-time. And the square of this wave function represents the probability to find a particle at some point, at some time. Okay? That's all. From special relativity, we learn that there's a maximum speed that we can reach. We cannot go beyond the speed of light, which is c. And this gives us a new notion of causality. Two points that are separated by a distance that is higher than what this velocity can achieve cannot be causally connected. Cannot be some information translated from one point to another. Both theories have more characteristics, but I point out these two, because when we try to put them together, we find that suddenly some inconsistencies appear. Okay? For example, if we consider a quantum particle that wants to go from one point to another that is separated by a distance higher than what light can reach, we find that the probability is not zero, the probability to find the particle in the point B. This is not possible. The probability has to be zero because these points cannot be causally connected. Okay? Another problem is that relativity gives us another relation between energy and momentum, which is quadratic. Suddenly, negative energies appear. This cannot survive under a probability interpretation because somehow this is related with negative probabilities, and we know that probabilities have to be positive. Okay? So, some other inconsistencies appear, so we need to add something else in the theory, not only quantum mechanics and relativity, but also the notion of a quantum field theory, a field theory. A field is a more complex object that allows us to solve all these inconsistencies. For example, the field is capable to explain the creation of a particle and the destruction of an antiparticle at the same time. So we do not have problems with negative energies, and we forget about the notion of probability, and we go into a field theory, which is more powerful. Okay? Then another very important instrument that we take advantage of is the presence of symmetries. Symmetries are very important in all physics systems, not only in particle physics, but here they are particularly exploited. We know that if one theory is invariant under some transformation, then the generators of such a transformation are constants of motion. So we are going to have conserved quantities that can describe the properties of our states. And this is very good because they simplify a lot the calculations and everything. For example, there are continuous symmetries in space-time, you know, translations, rotations, boosts, which are the same as rotations but generalized into the Minkowski space. These three kind of transformations form the Poincaré group. If we oblige our system to be invariant under this Poincaré group, we get three particles with defined mass, defined energy, momentum, and angular momentum. So only with the Poincaré group and obliging our system to be invariant under it, we can describe all this table, all this part of the table. We have three particles with some mass, some momentum, and everything. However, we know that we do not live in a free world. We need interactions. We need some particles. We need some interactions that describe how these particles interact. So, what symmetry could help to describe this kind of interactions? It's a very special symmetry, which we call gauge symmetry. Gauge symmetry is an old concept. Actually, when Maxwell was trying to unify electricity and magnetism, he found the freedom to choose one among many potentials. many potentials describe the same equations of electricity and magnetism. And this was called a gauge symmetry. And they found that the magnitude that was conserved under this symmetry was the electric charge. So somehow we know that this gauge symmetry, this gauge concept, is related to interactions, because potential is interaction, and the quantity which is going to be conserved is actually the charge of that interaction. So let's take advantage of this. Before that, just to recall what kind of maths we are going to find. We use the Lagrangian formalism. I am not very interested in the symbolic meaning of everything, just you to know that we use the Lagrangian formalism because it has three advantages. First, it is a Lorentz invariant quantity. It is the same quantity for all reference systems. Since we are using relativity, we want something that respects that kind of transformations, and this is very good. Another advantage of the Lagrangian formalism is that we already know it. We know it from classical mechanics. We know how to derive the equation of motion of the system, and we know everything. So it's a very familiar and easy way to do it. And finally, maybe the most important is that it exhibits in a very explicit way the symmetries of our system. I'm not interested either in the maths, just you to notice that only by knowing the Lagrangian, we directly know if it has symmetries and what are the conserved charges. Okay? I want to show you now an example of how to exploit the gauge symmetry. The symmetry who is going to give us the interaction. Just assume that this psi describes an electron field who is free, is propagating freely through the universe. Again, I'm not interested in the symbolic meaning of this, just you to know that this Lagrangian describes a free electron. This Lagrangian is invariant under this kind of transformation, which are gauge type. Okay? These transformations are called global gauge. You are going to understand in 1 second what it means. Okay? However, this Lagrangian is no longer invariant under this kind of transformations if this theta depends on the space-time. This is what we call local gauge. Okay? It's not invariant because the presence of this derivative term that has an extra piece that breaks the symmetry of the Lagrangian. So suddenly we do not have a symmetric Lagrangian. What can we do? We can assume the same theta in all the space-time, for example. But this is a very unnatural convention, to assume the same phase convention everywhere. Another thing we can do is add to this Lagrangian, to this free Lagrangian, another piece that exactly cancels this term. This piece, by construction, has to have another field, which is going to couple to the free electron, okay, like this. So this field can be also a propagating field. It can go freely through the universe, but its mass term is forbidden. So this means that this field is going to have a zero mass, because this term would break also this transformation. This field is nothing else but the photon. So we didn't do anything. I mean, we just assumed that there's an electron in the universe. And then we said, our Lagrangian has to be gauge symmetric. Then you have to have the photon. We have included the interactions into our theory. Okay? And this is the basics of the standard model. The standard model is described by these three interactions: the strong, the weak, and the electromagnetic. And each interaction is going to have a gauge symmetry, obliging our Lagrangian to be invariant under such symmetries. We are going to get the bosons that describe the interaction, and that's all. This model actually can be written in this term. We can unify the electromagnetic and the weak interactions because they affect to the whole table, while the strong interaction only affect the quarks. Okay, okay. So the strong interactions, we want to get the gluon in this case. This is group theory, but just you to know that the strong interaction generators are 3x3 matrices. That implies that we are going to have 8 generators, so we are going to have 8 gauge fields. We are going to have 8 gluons in our table. Then these matrices don't commute. This means that gluons are going to have self-interactions and also that the strong charge is unique. It's the same for all particles. It's not that like the electric charge. The electric charge, the electron have different electric charge than a neutrino, which is zero electric charge. This charge is the same for all particles. All particles interact with the same intensity under the strong interaction. And, of course, these bosons are massless to respect our symmetry requirements. They have mass zero. Let's go to the weak interaction. We have 2 by 2 matrices as a generators. 2 by 2 matrices in the basis, which means that we are going to have 3 generators. We are going to have 3 gauge fields, the sigma 0, the W plus, and the W minus. These matrices, again, doesn't commute, so these fields are going to have self-interactions, and again, the weak charge is unique. It's the same for all particles. All particles interact with the same intensity under weak interactions. Again, these bosons have to be massless in order to respect our gauge symmetry. These bosons, in principle, don't have a mass. Again, with the electromagnetic, is what we did before. We have one generator. This means that we are going to have only one gauge boson, which is the photon. This generator is a 1 by 1 matrix, is a number, so it commutes. This means that photons don't have this kind of terms, don't have this kind of self-interactions, and in this case, the electric charge is arbitrary. We have to fix it for each particle. We can find different electric charges. And again, the photon is massless. So we have completed the table in a very easy way. However, there's something wrong, because we know that these guys actually have a mass. Okay? So we are doing things in a proper way, but we are forgetting something here. Actually, I didn't tell you all the story, but also for the structure of the gauge symmetries, all of these particles cannot have a mass. So we have the right theory, but everything is massless. In the case of the photon and the gluon, it's true. It's experimentally tested. But in this case, it's not true. So what is this extra piece? Is the Higgs? This is the Higgs sector. Let me explain you what it consists. We want to give masses to the particles, so it means that we need to break the gauge symmetry. However, we know that if we break the gauge symmetry, we don't have the interactions, because it's the symmetry who have given us the interactions. So how do we solve this dilemma? This dilemma is solved by getting not symmetric results from a symmetric Lagrangian. We are going to explore the idea of spontaneously broken symmetry. Imagine that we have a Lagrangian, which is invariant number 1 symmetry, but the ground state is defined by a degenerate number of ground states. There is a degenerate number of states of minimum energy. In the moment that we choose one of these states, we are going to break the symmetry in the vacuum. In the ground state. So there is an example with the ferromagnet. The ferromagnet is a system whose Hamiltonian is invariant under rotations. However, the ground state has spin-oriented states. And not only the ground state, but also the excitations of that ground state are not rotation invariant. But the whole Hamiltonian remains invariant. Okay? So the ground state of our theory, of our system, is the vacuum. So we want a symmetric Lagrangian, but a non-symmetric vacuum. And how do we achieve to have a non-symmetric vacuum? Introducing a field and making it interact with the vacuum. Okay? In the moment that field interacts with the vacuum, it gets what we call a vacuum expectation value. Suddenly, the vacuum is not empty anymore, but it's plenty of these B's. It's not zero, but it has some value. We have chosen a particular ground state. Okay? This field is the Higgs, and when we make it interact with the vacuum, we get all of these bits, that are gonna fill the ground state. This is the mass term of, for example, a down quark. If we want to give to down quarks a mass, we make them to interact with the Higgs. And the mass is defined by the product of this B by this C. Okay? And that's how the quarks and the rest of the particles get a mass. Let me explain you in a more graphical way. This is our old vacuum. The old vacuum is empty. Now it's not empty anymore, but it's plenty of it's plenty of a B, it's plenty of something that interacts with the rest of the particles. And the mass is defined by the intensity of that interaction with the vacuum. If you are a particle that don't feel this interaction, your mass is going to be zero. Is the case of the photon. But if you are a particle that feels this interaction, the intensity of the interaction is going to define your mass. This is the Higgs mechanism. So we are very happy because we have completed the table finally, but we didn't see the Higgs yet. We haven't seen the Higgs yet. So we built a very expensive machine in Geneva, which we have called the Large Hadron Collider, to find it. Okay, it's the last particle that we want to find. The LHC is an accelerator. It accelerates 2 proton beams to make them collision and try to analyze in these 4 detectors all the pieces that are inside or can be generated from this collision. It's 27 kilometers. Okay, this circumference is 27 kilometers and is 100 below ground. There are superconducting matters that are frozen at 2 Kelvin. Actually, is the coldest place in the universe because even the extragalactic space is a bit hotter. So we have the coldest place just in Switzerland. Then we have the 2 proton beams colliding at 7 tera-electron volts, which means 10 to the 12. It's a lot. There's an ultra vacuum. Actually, the pressure there is 10 times less than the moon. The protons travel at a speed very close to the speed of light. They make 11,000 rounds per second to this circle. The magnet cables are 10 times thinner than the human hair, and they have a total length of 10 times going from Earth to Sun. Magnets retain energy equivalent to 60 kilograms of TNT, and just to give you an idea, the data of one of these experiments can be recorded in 100,000 DVDs per year. So it's kind of a very big machine. Very big machine, not only for the Higgs, but also for many other things, because the standard model is not the final theory. The standard model explains very well some things, but we know it's incomplete. We know there's something else beyond. Actually, it cannot explain the 95% of the universe. The matter we know is only the 5% of the universe. The rest is a combination of what we call dark energy. We don't know exactly what is it, and dark matter. Dark matter is something that doesn't have interactions with anything, but with gravitation. We know that it's there because it has a mass and we feel it. The standard model is not capable to explain the matter-antimatter asymmetry in the universe. Matter-antimatter asymmetry is that when the universe started, there had to be an asymmetry between the amount of matter and antimatter. Because matter and antimatter have a property that when they interact, they give nothing. They only give light. And if we are here, it's because there had to be a remnant of matter, an extra piece of matter that didn't die in this collision at the beginning. I didn't tell you this, but the Higgs mechanism is not able to give masses to the neutrinos, and we know that the neutrinos are massive, so we need another mechanism, a part of the Higgs, that explains why these species have masses, very, very small masses, but have masses. Also, the technical natural problem, which tries to answer the question why we have so different masses? Why we have one mass of one particle that is 100 times than another if they are given by the same interaction, if they are given by the same particle? The flavor problem, why we have these 3 replica of particles, why we have 3 families and not 4 and not 5. SUSY is a very famous theory beyond the standard model, and of course the LHC will help us to find out if it's reliable or not. Grand unification, trying to unify strong and electroweak interactions, of course gravitation, etc. So now I want to present to you a particular way to enlarge in the standard model, to add new physics to the puzzle, which is adding one more Higgs to the particle content of the theory. Actually, adding one more Higgs can help to all of these problems. So it's worth to study, because it's quite model independent. It's a very small assumption, only one Higgs more, and it can help to all these items. So let's go now to Higgs models. If you remember, the mass term of the particles is given by this. This is the mass term of the down quarks, this is the mass term of the up quarks, and the mass is defined by the product of B and C. If we add another Higgs into the game, we are going to have an extra piece here. By construction, it first has an advantage, and this advantage is that appears is the presence of complex numbers. Complex numbers are related directly with CP violation, with this asymmetry between matter and antimatter. So it's good to have new complex numbers, because these complex numbers are going to be new sources of CP violation, new sources to explain the matter and antimatter asymmetry in the theory. However, adding one more Higgs like that has some problems related with 2 characteristics of the standard model. The standard model has the characteristic that when we have charge currents, when we have a decay of a particle into another particle interchanging a charge, this means that we have to move from this column to this column. One particle can decay in another particle of the same symmetry, and also it can decay in a particle, symmetry no, family, sorry. It can decay in another particle of another family. However, in the neutral currents, we cannot move from this column because it's neutral currents. These kind of transitions are forbidden experimentally. And also the standard model is in agreement with that. In the 2 Higgs model, if we add another Higgs without any other constraint, these kind of transitions are allowed. And we don't want want this to happen. We don't to remove these dangerous currents from the puzzle. Then, adding one more Higgs, we have CP violation, but dangerous currents appear. Different models trying to avoid these dangerous currents have been developed. For example, we can assume that the masses of the new Higgses are very high. This is somewhat related with the fact that these new Cs, are going to be very suppressed. So we are going to have, dangerous currents, but very, very small. Another way to do it is assuming that these Cs are directly very small. We are going to have dangerous currents, but very small. The most famous way to do it is assuming that one of these Cs is 0. If one of these terms is 0, we are going to solve the problem. For example, we can do it as what is called the model 1, but making only the second Higgs to interact with particles. Or, for example, as the model 2 says, making the second Higgs interact with down particles and the first interact with up particles. We can play a bit with this. More models of these types are done, playing with leptons, etc. And under this kind of framework, no dangerous neutral currents appear, but also we lose the possibility of having new sources of CP violation, new sources to explain the matter and antimatter asymmetry. So this model has a lot of advantages, but we lose this possibility. And this is my work since 1 year up to now. is one model that we call the aligned to Higgs doublet model. The aligned to Higgs doublet model considers a third possibility, which consists in making these C's proportional. If you make these two C's proportional, at the end we are going to have only one C to give mass to the down sector and not two. And here a number. Okay. We actually success in this danger of neutral currents. We don't have this danger of neutral current, and we conserve the possibility of having new sources of CP violation. So we have a model which is totally reliable, and it's capable to help to explain the matter-antimatter asymmetry. As I said, this is the main advantage of the model. Also, a very important advantage is that it contains, as particular cases, all the models described before, because all the models described before are based in a particular case of disproportionality, and is that this is zero, and that's all. This model is general, but still have only a few numbers of new physics parameters. This is also an advantage because many models beyond the standard model have like 20 new physics parameters or 100 new physics parameters. They have a very strong new physics concept, but they are not predictive because they have so much freedom that they cannot say too much about a system. So we have only 5, and it's a good number. And this kind of models is model independent. As I said before, adding one more Higgs to the puzzle is a very small assumption, but it has a rich phenomenology. It has lots of consequences that can be used and incorporated in many models beyond the standard model. So we are going to have new contributions to the decays through this new physics that we are adding into the puzzle. And also, we have to take advantage of the experimental measurements to bound these parameters. These parameters cannot have any value. They have to be linear in order to be predictive. So, my research was based in first proposed the model and explained the theoretical framework and the implications of this 2 Higgs model. Then we took the new physics parameters and evaluated the impact in all known particle decays. Okay? Then we found some limits in those parameters and sized how big is the new physics contribution in a given decay. And then, of course, we had to put all the phenomenology together, and this is very interesting for the experimentalists because you have to tell them where to look for this new physics, how big it's going to be, where you cannot find it, etc. And, of course, compare with other models and still keep going. Now I just want to show you a couple of plots that are an example of how we bound these new physics parameters. For example, in the decays that participate the leptons, also the quarks, but the leptons, we can put all them together, analyze the new physics contribution, and try to bound the new physics parameter. This is a particular new physics parameter combination. We can find that this combination is bounded to this yellow area. Actually, the standard model is a point is here where these new physics parameters are 0, and we know that now we have more freedom. If something is detected here, our model is capable to explain it, while the standard model not. Here is the analog plot, but with another combination of parameters.
Sorry, what are these parameters? So
yes.
Masses of something or
yes,
energies?
These parameters, zeta u, zeta d, zeta l, are related with the C's, the couplings to the quarks to give masses. To give masses to the up quarks, to give masses to the down quarks, and to give masses to the leptons. We have new physics parameters because we are adding another Higgs, and these are parameterized by these zetas, zeta u, zeta l, and zeta d. And this Higgs is a new Higgs. It's not the standard model Higgs. It's the new one we are introducing into the theory. For example, in the decay of a kaon into another kaon, a kaon is a combination of quarks. We find, for example, that we can bound the mass of this new Higgs in terms of the values of this zeta u parameter. and we know where the experimentalists have to look for it. If we consider this decay, be decaying in S and gamma, we find again different combinations. Zeta D, zeta U, zeta D over the mass of the new Higgs, zeta D, zeta U over the phase. We have to play with all our degrees of freedom, and finally, of course, put all this information together, because this is not giving independent information. And now, to finish, I want to show you an example of how this model contributes to the matter-antimatter asymmetry of the universe, which is called CP violation. We detect CP violation in a particular decay by what we call CP asymmetries. For example, if we consider the decay of a B into a B bar, here we plot how our model enlarges this CP asymmetry. And we see that our model enlarges this CP asymmetry by almost 60 times. And actually, this is related with a very recent measurement that was done before summer in the V0 detector in Chicago. And there, they detected that actually in this system exists a CP asymmetry very different from the standard model. So, for example, in this case, our model could explain that separation from the standard model. Also, when we find this kind of enlargements, you can also bound the parameters. If this asymmetry is confirmed, the mass of the new Higgs will prefer to be low, and the mass of the zeta D will prefer to be high. Again, in the process B2S gamma, we find a CP asymmetry. The standard model asymmetry is very close to 0. So, if an asymmetry is detected in this system, our model is also capable to give an explanation. We need better measurements, for sure. And so, let me go to the conclusions. I have presented you the standard model of particle physics, which is a successful theory capable to explain the basic contents of nature and the interactions. This model has some limitation and needs to be complemented with new physics. I have showed you a particular example of new physics, which are the two Higgs models. These models are based in a very simple assumption that help to solve many problems of the standard model. And in particular, I presented you the aligned to Higgs model that results in a very general realization of a two Higgs model, which is at the same time reliable and able to give contributions to CP violation. So, as I try to convince you, we don't believe only in a Higgs, but two, and that's all. Thank you.
Any questions?
Before you do the reduction, you have two complex numbers that introduces and help you a lot. But then you do the reduction assuming that they are proportional. So somehow you are reducing your complexity of the problem.
Yes.
Don't you lose some other possibilities also with that?
Yes, the general two Higgs model is good because it has more sources of complex numbers, that's good. But actually it has too many parameters and too many sources. So for sure, under that point of view, the general model is better because it has more sources. But it allows for dangerous currents that doesn't exist. So our model is something in the middle. It's not very basic that it loses the possibility of having complex numbers, but at least it has some source. Not so many, but some source.
Of those 5 parameters that the model has, how many are you able to identify with a single number? I mean, how many degrees of freedom are still?
5.
No, yeah, but I mean, with the empirical data, with real data, how many are you able to put a number on them?
We only can find bounds up to now.
Okay.
For example, the zeta u it only can be from 0 to 2, which is a very good bound actually. But zeta d is 0 to 50, and the mass of the target Higgs is bounded from 80 to, we don't know, it can be actually very massive. Only bounds.
The fact that the two new particles are proportional one to the other, what does imply the properties of the particles? I mean, these two Higgs particles have to have some specific properties related to the other because of this?
it's not that these particles are proportional one to the other,
No,
but
I mean, the field that you take are proportional, but then
Yes.
it should reflect in the properties of the particles that you...
yes, the property that you are going to see is, for example, that you don't have this dangerous current. But actually, what is proportional are the couplings or these particles. So what you lose is, as he said, having another source of complex numbers.
So if you have two independent particles, why they should have a coupling which is proportional one to the other? I mean, what would explain that proportionality?
What mechanism would explain
Yes.
the proportionality? Some high energy. You can have different mechanisms to explain it. Usually, when you make such an assumption, which is an assumption, you say that some high energy physics is giving you this proportionality. Actually, we wanted to put this only as a phenomenological possibility. What happens if they are proportional? But in principle, we are not so interested in finding the underlying explanation for that proportionality, but of course, yes, I mean, it's worth to do.
And for example, the second Higgs should have more mass than the first Higgs? Or...
In principle, the standard model Higgs should be the lightest, because, yeah, and the other ones should be higher. But actually, okay, I didn't say, but when I said that I include another Higgs in the game, actually, at the end of the story, it means that we are going to have 5 Higgs. Anyway, one of those Higgs is charged, is not neutral. And this can be lighter, for example, than the standard model.
The one question I don't know if it makes any sense, since you presented so nicely on me, anyway. It's about this symmetry breaking. So you say that you have the Lagrangian, which is symmetric. However, the solution is not symmetric.
Yes.
And that's spontaneous symmetry breaking. So well, in nonlinear dynamics, that typically happens because you have a symmetric solution that undergoes an instability, and then depending on the initial conditions, you will get one solution or the other. Does it have anything similar here, or is it just you pick one? So which is the solution we are sitting on? So
You can choose the solution at the end, but they are. We say that they are the generic. They are the same.
yeah, exactly. But
They give similar vacuums. Let's say.
yeah, exactly. But you are sitting on just one.
Yes.
So
What happens is if you sit in another?
no. Why
sorry.
you are sitting on that one and not another? Does it come from an instability where you are in a symmetric solution that can somehow become unstable, and then you get one as a particular realization of initial conditions or things like that, or does not make sense?
No, for sure makes sense. But I'm not sure if I understand. I mean, all particles get mass because we choose one state. But if you would choose another, that would be the same. I mean, it would happen.
You get the same masses,
yes.
same masses, same everything.
Yes, because the ground states are the generic, that represent the same. Are not.
Yeah, but the symmetry breaking, where does it come from? So there is also symmetric solution of the problem, or not?
The symmetry breaking. Can you repeat?
So you have a Lagrangian which is symmetric.
Under one, yeah.
But then the solution is not symmetric.
Exactly.
Exactly. There is also a symmetric solution of the Lagrangian?
Yes.
But these are
Yes. Actually, sorry, I don't think it's very far away. I didn't. It's a bit far away. Okay, this is a symmetric solution when you are here, which is unstable.
Which is unstable.
Yes.
Yeah.
Mm-hmm.
And what's that?
Okay, it's not unstable. It's only that it's not the minimum.
It is unstable.
No, it's unstable.
If you have some noise, then
If you put, yes, if you
if
introduce a perturbation, then you go here. Yes.
deterministically it is
Yeah,
stable.
exactly.
Okay.
Let's say, is there a parameter that goes from a one-well solution to the two-well solution? Is there a parameter in the model that?
This is just the solution when all particles have zero mass.
Yeah, but he's asking, is there a parameter that allows you to go, let's say, from a parabolic
To this,
symmetric Lagrangian to a quartic? You know?
we assume that the potential of the Higgs particle is this.
Assume.
Yes, but it's an interesting question. for sure we could have an unstable solution, although it would have zero masses to the particles. But yes, it would be a possible, I think so, in principle, yes.
I mean, I understand you study a particular two Higgs model. And now, what are the alternatives to models with two Higgs?
Actually, having two Higgs is a starting point. You mean in order to give masses to particles, or in general to go beyond the standard model?
Well, you put two Higgs models solve all these problems, and you make a list of problems. Okay?
Yes.
And what are the alternatives to this assumption of two Higgs?
For example, many models beyond the standard model takes advantage of having one more Higgs. So it's quite present everywhere. But you can also have extra dimensions, which assumes that we do not have only 4 dimensions but one more. Then you are capable to explain also masses without using any Higgs, for example. You have also string theory. You have also supersymmetry, but supersymmetry needs 2 Higgses, for example. You have technicolor, which okay, you have different alternatives to actually, for example, string theory can explain almost all problems. It also can incorporate gravitation, but it's a theory that is not predictive at all because it has many parameters. But there are alternatives, for sure. But this is a reliable, this is a very nice way because it's a phenomenological proposal that is actually inside all of some other proposal.
The answer to a previous question when you said that there would be actually not one more, but 5 Higgs and one would be charged with less mass. But then it has a lower mass, and what should have been observed already?
No, because maybe you are not doing the experiment well. Maybe you are not. No, maybe you are not. Maybe your instruments are not. You are not trying to find it. If you don't try to look at it, you do not see it. You have to. But
the less massive no charge one will be detected by the new experiment or not?
It would be nice, yes. I mean, actually, the masses of these new Higgses, in principle, are inside the range of what the LHC can achieve. They can be very massive, for sure, but in principle, yes.
So what happens if there is no Higgs?
That we have a lot of work, or they have a lot of work. Yes, that's another possibility. There are models that implement masses to the fermions and to the bosons in a normal way. But if we don't find a Higgs, then it's a problem.
The neutrinos don't get the mass through these mechanisms.
The neutrinos have zero mass, not only because of the gauge symmetry, but also for some construction of the weak group. It's a property that.
So even the Higgs is found in the mass of the particles of the neutrinos will not be used.
No, we need another mechanism.
There is an alternative for the mass of the neutrinos?
Yes, we can assume that exist fermions. These particles are assumed to exist only in. They interact weakly, but only with one, let's say, spin. Only one way to. We say that they are left-handed. They only have one kind of coupling. If we assume that there are right-handed neutrinos, which is not in the theory, they can get masses through the Higgs mechanism. But we need to assume that they exist. I didn't want to enter in details, but it's something by construction of the theory.
Any other questions? Okay, now let's thank Paula again.